All right, from current slide. Okay, before we get started today, let's just go over a couple of things. Number one, first thing I want to do is give you the things that I may have missed giving you earlier, okay? As far as you know, you have received, this is going back at least as far as I can detect, okay? Y'all did the electromagnetism lab, and I gave you electromagnetism test, and y'all returned some of those to me. So I know those have been given. Okay, after we did electromagnetism, then at some point we did electromagnetic induction. That was the last chapter. So let's come back to that in a minute. In fact, I think I'll change the order of this. Okay. Electromagnetic induction. I'm going to move that further back. RC times move that further back. Okay. And then we got test 6. This is the one I should have given you that was at the end of topic 20. Make sure that's right. Topic 20, a uniform. Did you get this test? Yeah, now the test number is probably wrong. Okay. Did I give you this? This is the first half of the lab. I don't remember. You weren't here last time, so I don't know if you got it or not. Did you? No. Okay. So that's going to be the first half of the lab tonight based on that chapter that test was. Okay? That's electromagnetic induction. Okay? Now, so there's test 6. It says test 6. Okay. But that was topic 20. Okay. We finished last time. I should have given those out last time, but here's what happened. I took them to be copied the day before, and she either was out sick or something, and she never got them copied. And when I left, that came in the next day, they were in my box. So she came in. So that's why I didn't have it done.
So no one back.
What's that? No. I don't think so. That's what I was trying to remember. I've got the topic 21 test, which will probably be the last one. And we'll see if we got there tonight or not. But here is test topic 22, which was the nature of light. Okay? Did you get this one?
Yes, I just turned that into you.
Okay. All right. I thought I had given those out. Okay. That was topic 22, which we did after we did electromagnetic induction. Okay. And then y'all did the Ray lab, you know, the mirrors.
Yeah.
Okay. So you were there for that. Mm-hmm. This was the one on topic 23. I don't think y'all got this one because that was the one I was making out. Did you get that? Okay, so there's topic 23. So now you're up to date with where we are. Okay.
Just Monday, sir?
No. Okay, okay. Remember we did 2 chapters on light. Mm-hmm. We combined the labs to one lab for the 2 chapters. The first chapter was the one on nature of light, and this was the one on mirrors and lenses.
Okay.
And I didn't have this one. This may be the one she had. I don't remember. One of them I found in my box the next day after class that night. And she came in early and did them. So she hadn't done them the day before. That's why I couldn't give them to her. Whether it was that one, okay. So now I think you're up to date. We're going to do topic 21 tonight. If we don't finish, we'll finish on on Monday, and then we'll do the lab. You've got the first half of the lab there. After we finish this topic, then I'll give you the second half of the lab, and that's going to be it. Okay, so I think you're up to date. I don't know about the rest of them. All right, finally we're loaded. We're ready to go. Let me go over this though. You already mentioned paper topics. Please get those done. If you get it to me today or tomorrow, you still get a bonus point. If you get it to me Monday, you just get your score. If you get it to me Tuesday or later, you start losing points. Okay? Monday in class, I'll return every paper that's been turned in so far. The woman who's out said she's emailing me a bunch of stuff today. I won't be able to check it until tomorrow, but hopefully I'll get it and grade it over the weekend. And then Monday I'll be able to return everything to you. Whether she turned it in or not, I'll still be returning it to you. Okay, you know about sheet of course evaluations. Okay, have you already done yours or not?
No,
Not yet. Okay. Yeah, it was Ryan that did it. Okay. Okay, next. Oh yeah, the grading. I don't know if you heard that or not, but basically from Tuesday a week ago until now, I've not been able to get graded but just a little paper here or there when I was waiting in between other things because I was working on, well, Wednesday of last week I was in class all day so I couldn't grade anything. Thursday I was working on our planning meeting stuff, getting all that together. One of the instructors still hadn't got me his stuff. He didn't get it to me until Friday, which was my day off, so I had to put it together with the rest of it over the weekend, so I couldn't grade over the weekend. Finally got that sent off Sunday night, and then yesterday, on Monday, I was in class all day, so I couldn't get any grading done, and then Tuesday, I was over at the hearing, and that ate up 2 hours of office hours, so I didn't get any grading done. Well, I got a little bit done while I was waiting for the meeting to start, maybe 1 or 2 papers, that's all. And then, yesterday, I thought I was going to be able to catch up some in the afternoon, but people came by to register and a variety of things, and I had to run off all the labs and tests for everything today. So that ate up most of the rest of my day. So there's my sob story. You know, it's really sad, isn't it? And now we'll pick up on topic 21, alternating current circuits and electromagnetic waves. Okay? AC circuits. Alternating circuits power everyday electrical appliances. Okay? This projector is alternating current. Everything that comes out of the wall is alternating, except if it goes through a box like that, that converts it to DC because the computer runs on DC. But this runs on AC. Okay? The lights are AC. Just about everything you plug into the wall is AC, unless it has a box that converts it. Like your cell phone chargers and things like that, they convert to DC. We'll look at various circuit elements in the AC circuit: resistors, capacitors, and inductors. We've talked about all these in earlier chapters. Resistors for DC was way back on Ohm's law. Capacitors may have even been before that, and inductors was in the last chapter, I believe it was. Last chapter. Okay, we'll also look at what happens when these elements are placed in combinations in AC circuits. Okay? Now, we'll start with electromagnetic waves. Electromagnetic waves, and let me make sure everything is following in the right order here. This doesn't seem to be quite in the right order. Let's see if they have the electromagnetic waves somewhere else in here. Power, transform, resonance, natural position, versus properties of electromagnetic waves. Okay, I think this is going to show up again at the end, but they're introducing them now. So we'll hit them now, but we'll pick it up later. Okay? Electromagnetic waves are composed of fluctuating electric and magnetic fields And the electromagnetic waves come in various forms. For instance, visible light that you see outside or that we produce inside, this is electromagnetic waves. Infrared rays, which you don't see unless you have special goggles and things to see them, but you sense those, that's typically heat radiation. Okay? Then we have radio waves, which you don't see or sense, but you can tune your little devices to them, and they pick up radio waves. X-rays are very high energy waves that you pick up, and those you don't want to be around too much because these are very high energy and can cause issues. Very low dosage, not very frequent dosage, usually your body recovers from that. If you're constantly being exposed to them, you can have some pretty severe consequences from that. Okay? So, why that was stuck in there, I'm not sure. Let's go to the AC circuit. Okay? And an alternating circuit, alternating current circuit, AC stands for alternating current. Alternating current circuit consists of a combination of circuit elements. They can be resistors, capacitors, and inductors. An AC generator, which are a power source. Usually the symbol for that is a circle with a wavy line. That's usually the symbol for a generator. Now sometimes I've seen books, and maybe even this one, so the power supply for AC in its most correct form would be something like that. It almost looks like a generator, a turbine, okay? But you'll still see them given the symbol that looks like a battery. If it's AC circuit, it's not a battery, but they'll give that as a power supply, okay? So that's going to be part of it, the AC generator sources. The other things, the resistors still look like resistors, the squiggly lines. The capacitors are parallel plates, equal length plates. If they're not equal length, if they're alternating long short, that's a battery. Equal length is a capacitor. And the inductor is a series of loops. Rather than jagged peaks, they're loops. That's an inductor. We'll see that when we get there. The output of an AC, or alternating current generator, is sinusoidal, okay, a sine wave, and varies with time according to the following equation. Okay? Now, this is talking in terms of voltage. You'll see it's very similar when we talk in terms of current as well. But the voltage also fluctuates because the current fluctuates. And the delta V is delta V max. Now, there is absolutely no reason that I see at all. Well, they do it in the book too. Delta little v is instantaneous voltage, and delta V max is maximum voltage of the AC generator. So why they put one lowercase and one uppercase, I don't know, but they do it in the book as well. So that's what it means. This is the actual voltage, and this is the maximum voltage. Okay? The maximum voltage is basically the amplitude of this sine wave. Remember when we did that trick? Okay? Amplitude was that coefficient went in front of the sine or cosine function. Okay? The argument here is 2 pi, what does F stand for, you know? Frequency times time. And that makes sense too, because frequency is measured in per seconds. Hertz per second. That's all it is. Time is measured in seconds. So a per second times a second would be dimensionless. 2 pi changes that from a number to a radian. So the 2 pi makes it a radian measure. Okay? Delta V is the instantaneous voltage, so that's a lowercase v, and delta capital V max is the maximum voltage of the generator. F is the frequency at which the voltage changes in hertz. And I think we've just doubled our class size. Here we go with FA. And either when we take a break or in the class or go to the lab or something, I've got to give you the testing and labs that I've already passed out so far. I got those sorted right before class. I was waiting getting started just because I was trying to get everything in an order. Okay. We're on page 688, very first page in topic 21. So here's a resistor in an AC circuit. Okay? Consider the circuit consisting of the source, AC source, that's your generator, and your resistor. That's all you got, folks. Okay? The delta V is the actual voltage, which is a sinusoidal voltage. Sometimes it's max, sometimes it's min, sometimes it's zero. It follows a sine curve. And here is the sine curve. Delta V max, that's the amplitude, the maximum voltage you get, times the sine of 2 pi, that makes it radians. Alpha is frequency, T is time. Frequency measured in per second, time in seconds. That makes it a dimensionless quantity. And the 2 pi makes that a radian dimensionless quantity. Okay. This is your delta V across the generator. That's the same as the delta V across the resistor. Okay, guess what? That will have a alternating current flowing through it because you have a constant resistor. Alternating current, voltage, you're going to have an alternating current as well. So that's where we'll go next. We're not there yet. The graph shows the current through, this does show the current through the voltage, and the voltage across the resistor. The current and the voltage reach their maximum values at the same time because all you've got, if you think about it, and I wish they had done these in a different way, because basically what it is, V is equal RT, V is equal to IR. So I would have the V as the larger and the current is the smaller. They did it the other way. It doesn't really matter, okay? But I wish they'd have done it the other way. It makes a little more sense. The current and the voltage reach the maximum at the same time because they differ only by the constant, which is the resistor. Which the resistor, if it's anything greater than 1, that should make the delta V larger than the delta I, or the I. Okay? The current and the voltage are said to be in phase with each other because they have their maxes at the same time, their zeros at the same time, mins at the same time, maxes at the same thing. They go through very similar patterns. The current and voltage are in phase. They simultaneously their maximum values, minimum values, and the zero values all hit at the same time. I just wish, because delta V is equal to I times R, it seems like it would make more sense that the V be the larger one. But you see, these are on different scales, so you can make them any scale you want to. It just seems like it would make more sense to make the delta V larger. Okay? Now, the direction of the current has no effect on the behavior of the resistor. Because guess what an alternate current is doing? What's the alternate current doing? What do they call alternate current? Alternating current. What's it doing?
It's generating electricity.
Is what?
It's generating electricity.
Okay, no, basically the voltage source is generating, okay, the electricity. Why do they call it alternating current? Because it alternates directions 60 times a second. It's not like an electron leaves the switch and goes up to the light, goes through the light, goes through that, and then goes back to the switch. Basically, it's an alternating field. The field is alternating at 60 times a second. So the electrons are doing this. That's all they're doing. They're never going anywhere in the line, just back and forth, back and forth, back and forth. Really pretty slowly, but 60 times a second, approximately, they're changing. That's why we call them alternating currents. Okay? Direct current, the electrons are going all in the same direction. Okay? Everything's in the same direction. That's why it's called direct. Alternating is because of otherwise. So it doesn't matter what direction they're going, because they're changing constantly. Back and forth, back and forth, back and forth. Okay? The rate at which electrical energy is dissipated is given by this. This looks just like it did in the direct current case. Rate at which energy is being dissipated, what do we call that? The rate at which energy is dissipated, or used, or produced. The rate of energy is called what? We did it in 201, we've done it in 202. It's what? Time rate of change of energy. Do you remember the lab that we did in 201 where you went up and down the stairs? Mm-hmm. Same work was being done whether you walked or ran. What was the difference? You remember the lab?
Yeah, I don't remember the difference.
What were you measuring? The time.
Yeah.
When you walked, it took longer time to do the same amount of work. Mm-hmm. When you ran, it took shorter time to do the same amount of work. What differed then?
The speed.
Yes, the speed did. And that was related to
the rate.
The what?
The rate.
Yeah, that is the rate. What is the rate of using energy?
Momentum.
Second?
Is that the momentum?
Okay. No, the momentum is the rate of change of momentum is what a force is. What is the rate of using energy? It's right here on the board. Power. The power is the rate at which electrical energy, or any kind of energy, is dissipated. Electrical energy dissipated in a circuit. This is the same formula we had in direct current. The only thing in direct current, usually we use capital I, right? So P is equal to I squared R. Okay. Now, I is the instantaneous current. So this is changing constantly, right? Alternating from max to zero to min to max to zero to max to zero to min to zero to max to zero, maximum to zero, 60 times a second. Okay? Constantly changing. So the power is really fluctuating too. Sometimes the current's zero, sometimes it's max, sometimes it's in between. The heating effect produced by an AC current with maximum voltage I max is not the same as that of a DC current of the same value. Why not? Why not? Why would it be different in an alternating current than a direct current?
The alternating current has a maximum value of like time.
It's at that I max here, and here, and here, and here, whereas the direct current is constantly at that. So the other times in between here and here, down here and here. So that's always changing. So if the direct current was here, and this one was here, there's just a lot less power on average than that. So yeah, it will be much less, or somewhat less. The maximum current occurs for a small amount of time. There was the answer right there. Small amount of time compared to direct current, which is constant. Okay? Now, what we talk about then is the RMS current. What does that stand for? RMS. Same thing it stood for RMS in 201 today. And what's that? RMS. What does RMS stand for? Root mean squared. Okay? Because the current's always changing, Okay, just think of this. The current's doing this. What's the average current for that? Sometimes up here, sometimes down here, sometimes up here, sometimes. What's the average? 0. Because for every time it's up here, there's an equal time it's down there. So, it doesn't make any sense to talk about the average current being 0. There's got to be a current. It's only little places. The nodes are the only place it actually is 0. The rest of the time you've got a current. So what we do, we square it so that the positive stays positive, but the negative goes positive. Positive stays positive, negative goes positive. But since we squared it, then we've got to take a square root to get, that's why you have a root mean squared. You square first and then take the root, okay? And you average that, and that's the mean part. So here is the formula for this, and this is basically what you got in AC circuitry. The I max, that's the maximum current that you can have in the alternating current when it's at its max. Divide that by square root of 2, which is 1.414. So that gives you 0.707 times the I max. Right? So it's less than the I max, but not a lot less. The alternating voltages can also be discussed in terms of the root mean square value. So that, and this would be the maximum voltages, right? Delta V max. The root mean square of that delta V would be the delta V max divided by root 2, which is the same as multiplying by 0.707. Root 2 is 1.414. 1 over root 2 is 0.707. Okay? Times the delta V max. Same formula, just the different, what you're multiplying by, either delta V max or I max. And that's not a theater. Okay. So here's the root mean squared graph. Here is the actual current. This is what I was showing before. See, it goes up and down and up and down. So the average of that would be 0. That doesn't make any sense to talk about the current being 0 on average. It's not. We talk about what the average root mean square. So what we do, we square this. So we're going to jump it up. But then when it gets to 0 here, we're going to square this. So it moves it up again. Then we square that. It stays up there. And square this. And it goes back up here again. So that's what we have, and then we take the average of those, and then take the square root, okay? So the average, the area under the graph of I squared is equal to the area under the red dashed line, okay? So the average value would be this. This would be the square root of 2 would be here, okay? So 1 over square root of 2 would be there. See that the I squared average would be up here. Half of that would be here, and then take the square root of that, and that would be I over root 2. Do you see that? You square the current, this current here, and that flips this up. This stays up, but it expands this. This one that goes negative here gets flipped up to be exactly like this one, and then this one's squared too, and then this. So the first thing you do, here's your squared value, right? The maximum value squared. Take half of it. That's obviously going to be the one we're interested in. Okay, so that is your I max squared, half of that, and that's what your I, the instantaneous voltage, the average of that is. So take a square root, and that gives you I over root 2. Okay? That's exactly where you get there. The average value of I squared is 1/2 I max squared. Okay? So then when you want to take the square root of that, that gives you the root mean squared. Okay. So let's go back to power. What is power again? What is power again? Yeah. The rate of what change? Being changed. Energy. The rate at which energy is changed. So the average power dissipated in the resistor is in the AC circuit carrying the current of I is this I squared max R. That's the average power. Now, why isn't the root mean squared? Well, good question. But that is the I max squared times R. No, that's wrong. I thought it couldn't be. This is I root mean squared, not I max. I said this is not correct. This is root mean squared. Now, the interesting thing about it, though, and I think what threw them off, and also, well, let's go back here. They're just not being very consistent here. Nah, I guess they are more than I thought. See, here it's little I squared, that's instantaneous, okay? And I thought that they made, and you see, yeah, this is where they did. This is instantaneous squared average, and then when they take the square root of it, they make it capital again. So that's the part that doesn't really make sense. The average value of I squared, little I squared, is 1/2 capital I max squared, and when you take the square root of that, that's your root mean squared, but they make that a capital I again. And it sort of doesn't make sense to do it that way, but that's how they do it. So if that works here, that's the P average is the I squared, the root mean squared current, squared, okay, times resistance. Then similarly, you get the voltage, okay? So here's the notation used in this chapter, okay? And this, I guess, is the reason they do it, okay? Your instantaneous voltage is delta little v. So little v means instantaneous. The current, instantaneous current, is little I, okay? The maximum value is delta V max, right? And the maximum current is, and that's a capital V, by the way, too. And this is capital I max. The root mean squared value, okay, because it's an average, not an instantaneous, they make that capital V too. Delta V root mean squared and capital I root mean squared. Okay? That's the one that was throwing me why they capitalized that. And then when they put the wrong index on it, that really threw me. But they corrected it, and they have it correct in the book. It was wrong on the slides. Sorry about that. It's correct on this slide. Okay, so what is Ohm's law in an AC circuit? The root mean square values will be used when discussing the alternating currents and voltages. The AC ammeters, that's alternating current ammeters, and voltmeters are designed to read root mean squared values. Okay, now all we've been using so far have been direct current. We haven't done any with alternating current, and I doubt if we're going to have time to. So don't sweat that. Many of the equations will be the same form as in direct currents. Okay? The Ohm's law for a resistor in an AC circuit will be just this. Delta V, and they put a capital V here, across the resistor, the root mean square value, will be I, the root mean square of the current, times the resistor. It also applies to the maximum values of V and I. So the same thing would be if you put little v here, delta little v is little lowercase I times R. If you put capital delta V max, will be I max capital times R. So you can just exchange them any way you want to, as long as you keep root mean squared with root mean square, V max with I max, and instantaneous velocity with instantaneous current. Okay, does that make sense? Okay, now let's look at capacitor. Oh, wait. There's a quick quiz, 21.1. Which of the following statements can be true for a resistor connected in simple series circuit to an operating AC generator. Okay, which of these following statements can be true for a resistor connected in simple series circuit to an operating AC generator? The first one. Y'all got your books, or at least one of you do. Okay, the A part, the average power is equal to 0. Believe it or not. And average current is 0. Okay, sort of have to go back and see what their average power. No, average power is related to root mean squared current, not average current. So I would say that itself will rule that out. Okay? B, P average equals 0. Still don't believe it. And I average is greater than 0. Not likely. Okay? C, P average is greater than 0. That's sounding better. And I average, if you did your average of your instantaneous current, sure enough, that would be 0. We just don't use that, but it would be. And then D, P average would be greater than 0, and I average greater than 0. So which one looks like it's most likely? It looks like C. Let's see what they say C. Okay? And this is topic 21. Quick quiz. Number 1 is indeed C. Good for them. Now, there is a good example there, 21.1. What is the root mean squared current? I would say good one to look at. Okay? There's an applying physics 21.1, electric fields and cancer treatment. That's again a really interesting one. And I think they say here electric field therapy is especially promising for the treatment of brain tumors because healthy brain cells don't divide and therefore would be unharmed by the alternating electric fields. Research on such therapies is ongoing. So it's a pretty good application. Okay? Now we move to capacitors. It's 21.2 capacitors in an AC circuit. AC stands for? Alternating current. Consider a circuit in which an alternating current source, there's your power source, and a capacitor. Okay? Now here's your delta V. Is your delta V max. This is instantaneous change of voltage. This is your maximum change of voltage, sine 2 pi ft, just like we saw before. That hasn't changed. The voltage across the generator is the same as the instantaneous voltage across the capacitor. But what does a capacitor do when you put a voltage across it? You recall? Direct current? What does the capacitor do? Back in a much earlier chapter. What happens to a capacitor?
What was the question?
What happens to a capacitor in a direct current, not alternating current, direct current? That's the same thing, only you had a battery here, not a generator. What would happen if you set that up? Pardon me?
I don't remember.
Okay. But you would have the current, remember, direct current flows in one direction. So the current, say, would flow this way and start building up charge here, deleting charge here, taking it here. And so at first you would have a current, but then as you build up charge here, the current would decrease until it goes to 0. You had a question that asked this very thing on one of your tests. My memory is both of you got it perfectly correct. At the very beginning, your current's at the max, and the voltage is whatever it is. The but then after a while the current goes to zero. Okay, initially the voltage across here is zero, but anyway, it goes, and so after a while it charges this, and then it sits there and does nothing else. This voltage across the capacitor would be the same as voltage across the battery. No current flows because everything's equilibrium. So guess what happens if it's alternating? Well, wait. It starts charging and then discharges. It charges and discharges. It charges and discharges because it's alternating current. So it never is static like it is in a direct current state. Okay? So this creates something that's quite different. Resistor looks just like it does. Capacitor is very different. Okay? Now, the current starts out at a large value, okay, and charges the plates of the capacitor, just like it did in the DC circuit. There is initially no resistance to hinder the flow of the current while the plates are not charged. However, as the charge on the plate increases, then the voltage across the plate increases, and the current flowing in the circuit decreases, just like it did for a direct current, right? Right? Okay? Now, what happens next? The current reverses its direction then, okay? And now the voltage across the plate decreases, so the plate loses the charge they had accumulated. The voltage across the capacitor lags behind the current by 90 degrees. You see this? If your current starts off at a maximum, the voltage across the capacitor, okay, this is measuring the instantaneous voltage across the capacitor and the instantaneous current. When the voltage is maximum across the capacitor, when the current is maximum across the capacitor, there is no delta V across the capacitor. When the current goes to zero, you get maximum voltage across the capacitor, right? Right? And then when the current goes to a minimum, the voltage goes back to zero. When the current starts increasing again and goes to zero, the voltage goes back to a minimum, okay? And so you see everything lags by 90 degrees, okay? The voltage reaches maximum 90 degrees after the current reaches its maximum, so the voltage lags the current. Now this is the voltage across the capacitor, okay? Voltage across the capacitor. Okay. And just like we saw in direct current, they're out of phase. Not directly out of phase, but 90 degrees out of phase. Okay? The impeding effect of the capacitor. Now that sort of acts like a resistance, but it's not quite a resistance. It's an impedance. The impeding effect of the capacitor on the circuit, in an AC circuit, is called the capacitive reactance. Okay, the capacitive reactance, and is given by this formula. Okay, this is capital X is called the capacitive. Well, capital X is reactance. Okay, the sub C means capacitive reactance. Okay, you understand the symbology here? Do you understand the symbology here? Okay, the reactance is X, the capacitive reactance is X sub C. What is that? It's 1 over 2 pi frequency times the capacitor of the capacitor, so the capacitance of that capacitor. Okay? Now frequency is given in per seconds. So this is in the denominator, so it's sort of like you have a second in the numerator. Okay? Capacitance. Do you remember what capacitance is? It is measured in farads, but if you go back to capacitance, and I can't remember exactly the chapter number we did that, topic number that we did that. Here we go, topic 16. Topic 16. What capacitance is charge per volt. Charge per volt. That's capacitance. So, this is per second, right? Frequency, right? Times charge, which is a capacitance, which is charge per volt. When you have charge, that is coulombs per volt. Well, a coulomb per second, which frequency is per second, that would be a current, okay, times volts. So what we have there is 1 over a resistance. Because voltage times current is, no, that's not right. Sorry. Okay, I'm sorry. This is current divided by voltage. Well, 1 over current divided by voltage is voltage divided by current, and resistance is called, so this is still measured in ohms. X of C would be ohms. Just like resistance is for a resistor, reactance is for a capacitor. Okay, that would be measured in ohms. F is in hertz, which is per seconds. C is in farads, which is coulombs per volt, and X of C would be in volts per current, volts per amp, which is ohms. Ohm's law for a capacitor in an AC circuit. We didn't have anything like this in a DC circuit. There wasn't any Ohm's law for it. So here we have delta V for a capacitor, the root mean squared change of voltage in a capacitor would be root mean squared current times the reactance, capacitive reactance. Okay? Make sense? Now the trouble and the difference here is that your change of voltage, root mean squared voltage, is 90 degrees out of phase with the root mean squared current. But the formula still works, even though they're out of phase. Okay? So just like we had Ohm's law for resistors in direct or alternating current, we have something like that for this, only this is capacitive reactance, which is also measured in ohms. That time the root mean squared current is the delta V for the capacitor root mean squared value of it. Okay? Make sense? So, now let's move to inductors. Okay, there aren't any quick quizzes here, so let's move on to inductors. These are inductors in an AC circuit. Like I said before, the symbol for an inductor is, what is an inductor, if you remember? It's a coil. Remember? So look at the symbol for it. Look at the symbol for it. It's a coil. A resistor resists motion. The inductor induces a counter motion. So consider a circuit consisting of AC source. There's your AC source. Delta V, instantaneous change of voltage, is your max change of voltage. That's capital V on that one, times the sine of 2 pi ft, just like we've had before. And that creates a delta V across the inductor. Now this will be at a certain phase. This may be at a different phase. Okay? That's the only difference. It's the same value, but it's going to be perhaps a phase change. So let's see how that works. Now, the current in the circuit is now impeded, okay, resisted, worked against. How else can you say it? by the back EMF in the inductor. Remember, as it goes through a coil, you set up a magnetic field, the magnetic or magnetic field, which reduces the tendency of the charge to come through it. That's called the back EMF. The voltage across the inductor always leads. The voltage across the inductor always leads the current by 90 degrees. So in a capacitor, the current leads the voltage by 90 degrees. In an inductor, the voltage leads the current. Well, let me say it the other way. In a capacitor, the voltage lags the current by 90 degrees. In an inductor, the voltage leads the current by 90 degrees. The voltage reaches a maximum 90 degrees before. So let's get started here. With a zero voltage, you're going to have, now this is in the middle of a changing thing. Here your voltage is changing at the maximum rate. You see it? Maximum pressure or your slope here. You see that? You see it? Do you see it? The voltage is changing the fastest right there. So that creates the greatest amount of back EMF. So therefore your current is negative there, trying to force it in the opposite direction. When your delta V max, delta V actual, this is delta V across the resistor, across the capacitor, across the inductor, sorry about that, is at the maximum, then that's when the change is the least. And when the change is the least, your current is zero, right? When your change is zero, the current is zero. And then, when the voltage is again at its max, but going in the opposite direction, now the induced current is the maximum going in the forward direction. Again, I don't like that they made the currents look so bigger. I would have reversed the order, but it doesn't really matter. Okay, and then when the voltage is at its minimum here, again, its change is minimal, so that makes a zero current across the inductor there. And then when the voltage is at its maximum change here, that creates, but it's in the positive direction, the back EMF is in maximum in the negative direction. And it continues like that. Okay? So the voltage leads the current by 90 degrees in an inductor. In a capacitor, the voltage lags the current by 90 degrees. Okay? Does that make sense? All right. Now let's look at inductive reactance and Ohm's law in an inductor. Okay? The effective resistance of a coil in an AC circuit is called its inductive reactance. Now, what symbol do we use for reactance?
Sorry, I didn't hear you.
What symbol did we use for reactance?
I'm not sure.
Say again? What did you say?
Are you talking about the circle with the...
No, that is the symbol for alternating voltage. Okay? I'm talking about what symbol, what letter do we use to represent reactance. We did it for capacitive reactance just 2 or 3 slides ago. Say again? Yeah, the capital X. So it's capital X, but this is not capacitive reactance, it's inductive reactance. So it's capital X what? Sub L, I would say I because of capacity, but L, that's the symbol for inductance. So capital X sub L, which is 2 pi F times your actual the value of the inductance. Now, what units do we use for inductance? This is a unit question. What unit do we use for inductance? We talked about it last time. What unit do we use for inductance? jump back to chapter 20. I have gone too far. Say again? No, that's current. Amperes is always current. What unit do we use for inductance? It's the topic 20.25 is self-inductance. And that's where they introduce L. It's a proportionality constant called the inductance of the device, which is a coil. That's why they use the squiggly lines there. The SI unit for inductance is it's on the middle of page 673. Okay. Did you find 20.5? Self-inductance? The next page over, about one page from self-inductance, almost exactly a page. The SI unit for inductance is it's bold-faced, in fact. Huh? Henry, named after Joseph Henry, an American physicist. We talked about him last time. Okay? So that would be, L would be in Henry's. Now let's take a look about what a Henry is. A Henry is a volt second per amp. A volt second per amp. Okay, sort of strange unit. A volt per amp would be the same as a volt per amp is, volt divided by current is voltage divided by current. Ohm's law. Y'all did a test on Ohm's law. You did a lab on Ohm's law. What does Ohm's law state? If I remember right, y'all scored quite well on the Ohm's law test.
What was the question? I'm sorry.
What is Ohm's law?
That's the voltage. The current is.
Say again?
The current is proportional to the voltage.
Okay. And what is that constant proportionality? Say again? Okay. Said the other way, it would be resistance. The way you said it would be 1 over resistance. But, so if you said voltage is proportional to current, then the constant proportionality would be resistance. So V is equal to IR. Okay? Voltage is equal to current times resistance. So therefore, voltage divided by current would be, if V is equal to IR, what would be V divided by I? Yes, it would be resistance. So a Henry would also be an ohm second, because it's a volt second per amp, which would be an ohm second, which is strange. Okay? So let's go back here and look at this. If this is a 2 pi times a frequency, which is measured in what? Frequency is measured in what? Hertz. And in fundamental units, what would that be? A hertz is a per second, just like it was 2 slides ago. Okay? And a per second times an ohm second would be a per second times an ohm second would be a, say again? A per second times a ohm second, ohm, because the per second cancel out. One, the second here is in the denominator, second there is in the numerator. They cancel out, that gives you ohm. So inductive reactance is also measured in ohms. Capacitance reaction is measured in what? Ohms. And resistance is measured in ohms. They're all measured in ohms, but they're not all resistances. These two are reactances. When F is in hertz and L is in henries, the inductive reactance will be in ohms. Ohm's law for the inductor would be just like it is for the capacitor and just like it is for the resistor. Delta V, and this will be the voltage across the inductor, the root mean square voltage across the inductor will be the root mean square current times the inductive reactance. Current times amperes times ohms equals voltage. Ohm's law all over again. Okay? Does that make sense? Just remember that the voltage here leads the current by 90 degrees. Okay? Example 21.3 shows a purely inductive AC circuit. All it's got in is an inductor. Well worth a read. Now we're going to move to an RLC series circuit. What do you reckon RLC stands for? RLC series circuit. What do you reckon that stands for? What is R the symbol for? Resistor. What's L the symbol for? I'm sorry? By the way, it doesn't start with L. Inductance. And what does C the symbol for? Say again? No, I is a symbol for current. C is a symbol for, it starts with C. Capacitance, exactly. So this is a series circuit with a resistor in series with an inductor in series with a capacitor. Now the order doesn't matter, but it's got these three. And sure enough, this is a resistor in series with an inductor in series with a capacitor. The resistor, inductor, and capacitor can be combined in a circuit, and it doesn't matter the order that you do. The current in the circuit is the same at any time and varies sinusoidal over time, because guess what this is? What does this symbol suggest? It's an alternating. That's a generator, okay? Alternating voltage and an alternating current. And that's the same alternating current throughout here and here and here, but now here it changes a phase. And it stays that until it is here and changes the phase. So they have this. Now your delta VR, these are little v's here, meaning these are the instantaneous voltage across the resistor, instantaneous voltage across the capacitor, the inductor, and instantaneous voltage across the capacitor. These three have to add up to the instantaneous voltage that's created by the generator. Okay? The current in the circuit is the same at any time and varies sinusoidally with time. Okay? Now, here's what's happening. The instantaneous voltage across the resistor is in phase with the current. So this is the current here. The magenta line, the purplish line, the reddish line, whatever you want to call that, there's your current, right? It's sinusoidal, that's a sine curve. Perfect sine curve, right? Okay. The delta V, instantaneous voltage across the resistor, is in phase with that current. It's at maxes at the same time, zeros at the same time, minutes at the same time, everything at the same time. Make sense? Okay? How about the inductor? What's true about the voltage in an inductor? Say again? It leads. It leads the current by 90 degrees. So if the current is here, that means since the inductor voltage leads it, that would be over here. So there's the inductor voltage here. So that's different phase from the voltage across the resistor. How about the capacitor? It lags the current in the So therefore, when the current is here, the delta V across, of the current would be back here because it was 90 degrees behind. So there is the current in the voltage, instantaneous voltage across the capacitor. Now, what's the total instantaneous voltage is sort of messed up, okay? Because it's got, these two almost look like they would cancel out, except they're not always the same voltage. You see that? I mean, there's no reason to think the delta V here is the same amount as delta V there. So if they were, then they would cancel out exactly, and the overall voltage would be just like the resistor. But that typically does not happen. All depends on the magnitudes of these things. So it typically will not happen. All we can say is the instantaneous voltage lags the current in the capacitor, leads the current in the inductor, and is in phase with the current in the resistor. And that gives you some sort of result down here at the bottom. Okay? The total voltage. And they just sort of made up one. There's no reason to put any credence in how that looks, except it is still a sinusoidal curve, but off more than likely by some phase angle. Okay? Now, what these diagrams are called are phasor diagrams. And these particular vectors are phasors. Okay? And here's the phasor diagram. To account for the difference in phases of the voltage drops, vector techniques are used. You can't just add. You have to add vectorially, right? What does that mean here? You represent the voltage across each element as a rotating vector called a phasor. Not like they fired on Star Trek. That's a different kind of phasor. Okay? Now, the diagram is called the phasor diagram, and basically your this is not a very instructive looking figure here, but it's okay. It's just showing that the Y component of your, but they show this as if that's the instantaneous voltage. I don't know why they show this. This is the delta V max. So at any point, this is right. When the delta V max is down here, you would have a 0 delta V. That would be when you're, yes.
Are we still having lag?
Depends on how far we get tonight. Okay. We got a late start. Well, first because nobody was here, but secondly because I was trying to get all the papers in order, and I found out one thing hadn't been printed, or at least I could find where it had been printed, so I had to go get those printed. But I think everything's in order now. Okay? So, and the lab is a paper lab anyway. I gave the lab for the first part last time. Did you get that? The last chapter we did, this is our topic 21. We did topic 20 last time. And topic 20 had a paper lab, and topic 21 has a paper lab. Neither one of them are big enough for a whole lab, so I said we'd add them together. And that would be the lab for these two chapters. Pardon me? Okay, well, I'll give it to you at the end of class. Okay. All right, so let's look at this.
Oh, you got it today.
Okay. You see, when this delta V was down here with 0, then your actual delta V was 0. As it goes up, your delta V climbs with it. This is going in a circle according to your frequency. Excuse me. This is going in a circle according to your frequency, and your delta V actual is what it is. So here we have a 0 component, up here this component, up here it would be the full delta V max, and then as this goes down to 0 again, it goes negative down here until minus delta V max, then back up here to 0 again. So this is what gives you your sinusoidal progress of that actual voltage. Your delta V max is going around like this. That's how we represent it in phasor. Okay? Now, that would be any one of these. Okay? Now, here's how we would start and set up. The voltage across the resistor is on the x-axis because it's in phase with the current. And the current starting out at 0. So the delta V across the resistor would start at 0. The voltage across the inductor is on the positive y-axis because the inductor the voltage leads the current in the inductor. The delta V across the capacitor is on the negative y-axis because the delta V lags the current in the capacitor. Now, notice here they put different magnitudes of the delta V, which makes sense because a resistor, it would just be really weird for the capacitor to have the same delta V by, for instance, as the inductor as the capacitor, and then they would cancel out. Typically they don't, and typically they wouldn't have the same delta V as the resistor either. Just depends on the size of these things. Okay? Now, what you start doing is rotating these things. Okay? But you can make life a little easier because the delta V of the capacitor, of the inductor, always is leading and is exactly opposite of the delta V of the capacitor, right? Let's go back and see the phasor diagram. See, the delta V of the inductor is up here. You see? Delta V of the inductor is up here. Delta V of the capacitor is down here. So therefore, at any time, and these go in, they rotate in phase, right? They rotate in phase, so this one always is opposite of that, right? Can you see it? Okay? So therefore, we can do delta VL minus delta VC and count that as just one vector because they're always opposite each other, okay? And then that would be, that one little smaller vector would be leading the resistor. Unless, of course, delta VC was greater than this, then that would be lagging the resistor, the resultant flip. Okay? So you just left to live with what you got there. So the resistor starts out here. The difference between the capacitor, the inductor, and the capacitor is going to be up here. That's if delta VL is greater. If delta VC is greater, then it would be lagging down here. Do you see that? Okay? And this would be your phase angle. A positive phase angle here. If delta VC was greater, then it would be down here in a negative phase angle. Okay? Resistor is always this way. Okay? So the phasors are added as vectors to account for the phase differences in voltage, and the delta VL, delta VC are on the same line, and so the next component is delta VL minus delta VC. Delta VL is larger, that's positive. If it's smaller, then that would be a negative down this way. Okay? But this is then the delta V max for the whole system would be this, delta VR plus the difference of those two. Okay? So that would be your delta V max, and that's what rotates with that phase angle. All right. The voltages are not in phase. So they cannot simply be added to get the voltage across the combination of the elements or the voltage source. Okay? So the delta V max, do you see this? Delta V max is equal to delta V R squared plus the difference between delta VL and delta VC squared, that difference squared. And the tangent of the phase angle is the opposite, which is delta VL minus delta VC over delta VR. V is the phase angle between the current and the maximum voltage. The equation applies to RMS values. We've been doing them according to max values. You can also do them according to the RMS values, root mean squared values. Either one, but just keep everything in maxes or everything in root mean squares, and you'll be okay. So, this leads to, now these terms are easy to confuse, okay? A resistor is measured in ohms, and reactance is measured in ohms. Resistance, the symbol is R. What is the symbol for reactance? What is the symbol for reactance? You didn't know last time either, and we said it. What's the symbol for reactance? No, that's inductance. That's resistance.
So what are you asking for?
I'm asking for the symbol for reactance. You answered it before. Pardon me? There's two types of reactances: capacitive reactance and inductive reactance. Same symbol is used for both. The subscripts change. X is the symbol for reactance. Okay? And if it's X of L, what does that mean? Inductive reactance, X of C, capacitive reactance. Okay? So the impedance, Z, goodness, can't have ever got enough symbols here, can also be represented by the phase diagram. Now, get this. Here is your resistor, always in phase with the current, right? Its resistance, we count as a vector here. And then the reactance of the inductor minus reactance of the capacitor, because those are always out of phase with each other, exactly out of phase with each other. So that difference makes the opposite side of the angle, and then this makes the impedance. The impedance is the overall combination of resistance and reactance, overall. And you do it the same way we did for current and voltage before. Z is equal to the square root of R squared plus the difference of X of L and X of C squared. And again, the phase angle is exactly like before, XL minus XC over R. Okay? Now, the question is that the same phi? It better be. Okay? So, actually I jumped a little ahead. Let's do quick quiz 21.2. For the circuit in figure 21.8, 21.8, that's this one back here, that circuit right there, okay? For this circuit in 21.8, is the instantaneous voltage of the source equal to A, the sum of the maximum voltages across the element, B, the sum of the instantaneous voltages across the elements, or C, the sum of the RMS voltages across the elements. Say again? C. Okay? The question is the instantaneous voltage of the source. Okay? I wouldn't think that instantaneous would be the sum of RMS. I would think it'd be more likely B, instantaneous. But let's see. 21.2 is indeed B. Okay. With one, I think, I'm sorry. I think that question could have been improved greatly if they had put one adjective in there. And that would be the vector sum. I don't think, that's what they intended, but they should have put the word in there, vector sum. It's not just adding the instantaneous voltages, it's the vector sum of those instantaneous voltages. Okay? So that, I think they could have improved that a little bit. Okay? Okay. All right. Now, for some reason, oh, there it is. Okay. Before we do the next quick quizzes, let's go to this slide. Ohm's law can be applied to the impedance. What was the impedance again?
What did you say?
What is the impedance? What symbol do we use for impedance? What symbol do we use for impedance? Z. Okay. And how do we calculate that Z? The square root of R squared plus X of L minus X of C squared. What do the X's stand for? Reactance, exactly. Reactance, and they're either capacitive or inductive. So what are the units for Z? Yeah, same units. Yeah, that is the impedance, Z. What are the units for impedance? Yeah, it would be the same as the units for reactance. What are the units for reactance? Ohms, exactly. Same as for resistance. So that's why we could use Ohm's law. But understand this was a vector sum, not an adding in any other way. The only thing that's added is the fact that the inductive leads, the capacitive reactance lags, right? So therefore, that's why you use X of L minus X of C to get that, because those are in line with each other but opposite directions. And that's why we use that to calculate the Z, and then you do that. The same formula could work if you had RMS voltage and RMS current, or instantaneous voltage and instantaneous current. That can be regarded as a generalized form of Ohm's law applied to a series AC circuit. That's an LRC circuit. Okay? Actually, for Yeah, LC, or just by anything. It's a generalized form of Ohm's law for an AC circuit. But you use impedance here. Now, why they have the same type of meanings, but you use different things. Resistance if it's a resistor, reactance if it's either a capacitor or a inductor, and impedance if it's the vector sum of all three. So here's a table that summarizes those. The impedance values and phase angles for various combinations of circuit elements. If all you have is a resistor, what's your impedance? If all you have is a resistor, what's your impedance? Just the resistance, exactly. What would be your phase angle? Zero, because that's in phase with the thing. What if all you had was a capacitor in a circuit? What would be your impedance there? X sub C, which would be named say again? Not resistance, that's R. X of C would be, X stands for? X stands for? I've answered it about 2 or 3 times already. Say again? Okay. X of L would be an inductive, what does X stand for? L is inductive. Reactance. Okay? So your impedance for just a capacitor would be the inductive capacitance. Okay? For an inductor, what would be your impedance? The inductive reactance. Inductive reactance. Okay? Oh, what's the phase angle of this one? Of the capacitance? Negative 90. What would it be for the inductor? Positive 90. Okay? What if you had an RC circuit? What would be your impedance? Square root. X of C squared, exactly. What would be your phase angle for that one? You need to give it to me in an inverse tangent. Inverse tangent of X of C over R. Okay? And that would be negative something between minus 90 and 100, because it would be down here. X of C is always lagging. R is in phase, so it would be something between that. You could have given it as an inverse tangent of X of C over R. I thought they were going to do it, but they didn't. How about an RL circuit?
It would be the same like the first one, that R squared.
Square root of R squared.
Yeah, square root of R squared. X of L squared.
X of L squared. And what would be its phase angle, or where would it be?
Between 0 and 90.
Between 0 and positive 90. How about an RLC circuit? What would be the impedance there?
root of r squared.
right?
So it's L to C.
Plus what? Not plus. Minus x of c squared. Quantity x of L minus x of c squared. That plus r squared, square root of that would be that. And where would the phase angle be? It would be somewhere between minus 90 and plus 90, depending on which is larger, x of L or x of c. It's negative if x of c is greater than x of L. It's positive if x of c is less than x of L. It's something between 0 and 90. And you can do it exactly by the inverse tangent of this thing over that thing. So in each case, an AC voltage not shown is applied across the combination of elements, that is the dots. Right. Okay. Now, surprised they hit Tesla now. Nikola Tesla was, I believe, Croatian. Yeah. Born in Croatia, spent most of his professional life as an inventor in the U.S. Guess who he worked with? Pretty famous guy in the field of electricity in the U.S. Thomas Edison. Nikola Tesla worked under Edison in Edison's lab, and for a while they were pretty good collaborators, I think. But it really didn't last too long. They were both very strong personalities, extraordinarily bright people, but they were very headstrong. Okay? Tesla sort of chafed at working under Edison, but Edison had the upper hand. He was native and Tesla was immigrant. Tesla had just was flowing with ideas. And he would pursue some, and, you know, a lot of them didn't work. Some of them did. Some of them worked quite well. But he wasn't really good at capitalizing on those, so he wound up basically being broke most of the time. He finally did leave Edison's lab. Their big argument was over which is safer, alternating current or direct current. Edison was convinced alternating current at such high voltages would be deadly, would cause all sorts of major problems. Tesla, on the other hand, said alternating current was the way to go. You can't get enough current through a DC line without burning up. I mean, it just, you know, he said it was just about impossible. Turned out that he pretty much, history shows his argument prevailed. But Edison was a better businessman and managed to still do better. But Tesla was an inventor, and when did he live? 1865, which was right at the end of our war between the states, though that was when he was back in Croatia, up until 1943. So what is that, 78 years old? Pretty good age for a person in that time. That was lived through World War I, which, by the way, was started because of the assassination of Archduke Ferdinand or something like that of Serbia. So it was right in his area, but he was in the U.S. by then. Lived through World War I, and I don't think he had to fight. And right up until beginning of World War II. Not the U.S. involvement, but Hitler's come to power. But he was in the U.S. and pretty safe there. Majorly, he was an inventor. Okay? He invented a whole lot of stuff. Key figure in development of AC electricity, and he was financed in that by a guy named George Westinghouse. And Westinghouse is now, you know, the Westinghouse appliances are named after George Westinghouse. He was a proponent of AC electricity too. Tesla was pretty much the brains. Westinghouse was pretty much the money. But he was plenty smart too.
The old book says that.
What's that?
The old book says that he was born in
Really? Yes, the new book says that too. They got this wrong here. Okay, so that is a 56. Okay, and he died in 43. So that makes him even older. My goodness, he lived to be 87, if I'm subtracting right. Wow, that is old for any time. Key figure in development of AC electricity, high voltage transformers. Okay, sure, too high voltage in houses could cause a lot of problems, but you needed high voltage to transmit the current, the power, and the reason you need high voltage is so you can reduce the line loss, which is caused by the current. So the higher the voltage, the lower the current. So he created these high voltage transformers, key element in development of those. He also transported electrical power via AC transmission lines. He beat Edison's idea of DC transmission lines. He certainly won that one big time. Quite a character. Okay? Before we move to problem solving, let's hit the next 4 quick quizzes. Okay? If switch A, and let's see, I don't think we have a figure for that, do we? I don't think so. No. So let me draw this. Here's your voltage source, a generator, going up to, I haven't drawn this very well, a place where you have a switch, B, and the switch right now is open, but when closed, it goes across a capacitor and comes down and rejoins here. And on from here, you have another capacitor. And from there, you hit an inductor. And there you hit a resistor. Why they put a light bulb, that's just a resistor. Oh, I know why. Okay, it is a resistor, but they want it to be a light bulb, so let me draw it as a light bulb. I think I know why. That's a light bulb by definition. Okay, down here we have a resistor and a break to another resistor in parallel. But that second resistor is connected to a switch at A. Let me clean that up a little bit. Okay. All right, this is switch A here. And then that carries us on back to the generator. Now, we draw the circuits like that, but really, if you have a generator, where it usually goes to, and we're not doing this, so don't sweat it, but usually they show that going to ground. Because you usually don't go back like you do to a battery. A battery requires a complete circuit back to the battery, plus to minus all the way around the loop. If you don't do that, nothing comes on. In a generator, it leaves the generator and goes to ground, and goes back to Mother Earth. That completes the circuit. Okay? So here's the setup. Okay? Now, if switch A, the one down here, is closed in this figure, okay, what happens to the impedance of the circuit? So we're starting with open. So with that switch A open, what do we have in the circuit? With switch A open, switch B open. We have a, what does this represent? What does that represent? 2 parallel plates, same size? Second? No. If they were different sizes, that would be better. This is the AC, so it has a generator here. That's our power support. These are 2 same size parallel plates. What is it? What's that? It's actually often called a parallel plate blank. We had it back several chapters ago. And we've had it already in this chapter. two parallel lines equal length. That represents a second. No, the generator is this. That's the generator. Okay? If you go back to page, well, whatever is near the end of 21.2. It's a figure 21.4, I think. I don't know if those numbers are the same. What's your 21.4 look like?
The RC series.
Say again?
The name of the topic is the RLC series circuit.
No. Figure 21.4, not topic 21.4. It's back in topic 21.2, near the end of it. A capacitor, two parallel plates. It's called a parallel plate capacitor. That's where we get its name. That's how we represent it. What is this thing called? Yeah? What does that represent? What circuit element? An inductor, exactly. Now this is just a light bulb. In reality that would be a resistor, but I don't think they're counting it as a resistor. What's the squiggly lines here? It's pretty ugly, but what's that represent? A resistor, okay? So with both switches open, A open and B open, we have an CLR circuit or RLC circuit, just an RLC circuit, okay? Now, that's what we have, okay? Suppose if the switch A is closed, when you had that operating otherwise, what happens to the impedance of the circuit? It what? Why does it decrease? You're right, it does decrease. Why? What does this produce? Say again? What does this produce? You already told me what that was. Okay, and if you have two of them like this, what are they called? Resistors in? When the two paths that go through resistors, what do we call that? If they were in line with each other, you call it something else. If they're parallel, I almost gave it away. This is a parallel, these two resistors are in parallel with each other. And what happens if you got two resistors in parallel? What's their effective resistance? This is back in the...
You're talking about the direction?
What's that?
Are you just referring to the direction that
Not directions, the magnitude, the amount of resistance. What is the effective resistance of two resistors in a parallel circuit? Does the resistance go up, go down, or stay the same? Anytime you have more than one resistor in a circuit parallel, you drop the resistance. The effective resistance goes as 1 over the other resistance. Remember? And so it actually reduces. The effective resistance across here would be less than the least of those two. So it actually reduces the resistance, effective resistance. If you reduce your effective resistance, then therefore you reduce the impedance as well. So you were right in that it was, the impedance was reduced, but the reason is because the resistors would be reduced. So let's see, that should be B, and this is 21.3. 21.3, sure enough, is B. Now, here is the next 21.4. Suppose x sub L, that's the, what is x sub L? Tell me. You've answered that several times tonight. X stands for what? Inductive what? X stands for what? The L stands for inductive. Reactance. If x of L, the inductive reactance, is greater than x of B, x of C, which is the what? Capacitive reactance, right. In figure 21.12, that's this one here, so the x sub L is greater than x of C, okay? Okay? Suppose that's the case. If the switch A is closed, what happens to the phase angle? Okay? What happens to the phase angle? Does it increase, does it decrease, or does it not change? Okay. Well, you're guessing right. Do you know why? Because the last one was decreasing? Okay. Here's why. Your x of L being greater than x of C, there's a difference like this, right? Your resistor is like this, right? Thinking of your phasor. But when you have the switch closed, the resistance, the effective resistance is actually less. So the sum of this and this would be down here. The sum of this and this would be up here. So the phase angle would be increased. At least it seems that way. Let's see if that's what they've got. That would be 21.4 should be A, we think. 21.4 is indeed A. Okay? 21.5. Suppose that x of L is greater than x of C in that figure. If switch A is left open, so you just have the original resistance there, and switch B is closed, what happens to the phase angle? Then you would have what? If A is left open, so you just have this, across this resistor. Okay, what happens when you close B? What does that give you? What does that give you? What is that called? What are these two things? Okay, that's what the reactance would be. Well, what are these things called? Two parallel plates of equal length. What does the C stand for? Inside X of C. These are your capacitors. These two capacitors, when they're like that, what do we call that circuit? They're not end to end. They're like this. What's that? No, it's not a battery. It's a capacitor. You got that right. These two are capacitors. But what kind of circuit is that? Each of them has a different path to it. What did you call this circuit down here? They're drawn like there. We've done this for several chapters. Look at them. How do they look? They look like they are not like this, but like this. The lines never meet. What do you call those? Two lines that go in the same direction and never meet. You call those two parallel lines. These are two parallel resistors. Well, that was open. That's no longer the case. You just have one resistor. These are called.
Did you just say it?
Second. They're also like this. What do you call that? Parallel. They're not resistors. What do you call two parallel plates the same length? Capacitors. These are two capacitors in parallel circuit. Now, what happens when you have two capacitors parallel to each other? Down here, the resistance decreases. And here, because you see you're charging this plate and that plate, so basically that makes it look like a bigger capacitor. Okay? So therefore it has greater reactance. Two resistors in parallel have a smaller resistance. Two capacitors in parallel have a greater reactance. Okay? So therefore, this is increased. Now they still say that X of L is greater than X of C, so it's still pointing up, but now that's an even longer line, but this is longer too. Let's see. My word, can we tell on that one? Let's see what it says. No, okay? It's X of L minus X of C. So X of L stayed the same length, but X of C got larger, so that reduced the X of L minus X of C, right? Therefore, and the R stayed the same, so therefore the phase angle reduced. I think you said, did you say increase before? Okay. I think that was the last one, though.
Yeah.
This one you hadn't said. This, the phase angle actually decreases. That should be B. Let's see if indeed that's true. 25. Wait!
Well, 21.5 is increase. 21.6 is decrease.
Yeah, but we were doing 21.5. If X of L is greater than X of C in this figure, if the switch A is left open and switch B is closed, what happens to the phase angle? And it says it increases. I don't believe it. Because if X of L is greater than X of C, I don't know what they're asking about. When this is open, it's like that one's not even in there. So here's your X of L, here's your X of C, and the difference is up here somewhere. When you put that in, it increases this one, but it's still less than that, so that makes the difference smaller. Okay, the R stays the same, so that should decrease the phase angle. I'm not sure I agree with them on that, but we'll let that go. Let's do 21.6. Suppose X of L is greater than X of C in the figure, and with both switches open, like you see there, a piece of iron is slipped into the inductor. Okay? During this process, what happens to the brightness of the bulb? It increases, it decreases, or it doesn't change. What happens to the brightness of the bulb? By putting an iron core in that, what you're doing is increasing its capacitance. It's inductance. And when you increase the inductance, you also... Oh, wait. Sorry. I know why the other one is B now. I'm sorry. I got backwards on it. If you'll notice there, if you go back to topic 21.2, I think it's equation 21.5, your X sub C, that's a reactance, capacitive reactance there, it's 1 over 2 pi Fc. So if you increase the capacitance, you decrease the reactance. And we did increase the capacitance, but it actually decreased the reactance. So if you decrease the reactance, then that made the difference there greater. So yeah, that was an increase. So I back up there. Sorry about that. I was just thinking of the capacitance, not the reactance of the capacitive reactance. So let's go to 21.6. Suppose X of L is greater than X of C, both switches open, piece of iron is slipped into the inductor. During that process, what happens to the brightness of the bulb? It's what? I think it decreases because you've increased the reactance of the inductor, because the reactance of the inductor is proportional to the inductance. And sure enough, that one is B, it should be, and that's what they got. 6 is B. All right, now, let's move on. Sorry. Boy, after the day of talking, 2 hours and 40 minutes for Cal 1, 2 hours and 40 minutes for Cal 2, and we didn't have a lab in Physics 1, so that was close to 3.5 hours, and now this is close to 3.5 hours. So it hasn't been quite that much, but close to it. So, problem solving for LRC circuits. Here are the stages. First, calculate the inductive and capacitive reactances XL and XC. Yes?
So we're not going to do the lab?
I might, if we finish the chapter, I'll give you the lab. It's a paper lab, so you can take it home and work at it, or we'll work on it and then get in on Monday. So many people are not here. I'm guessing we will work on it on Monday.
Yeah, because we did 21.4. And do you have the final for this question?
Pardon me?
The final?
What about it?
You have it made? So I can
Yeah, the test on this chapter is the final.
Okay.
Yeah.
Get both of them?
Pardon me?
Can I get the lab and the final?
Yes, but at the end of class, because we're still having class right now. I've got to find those things there in the stats somewhere. Okay, how do we calculate the X of L and X of C? Do you remember the formula for X of L? Fairly similar formulas. F, 2 pi F, L. Okay. Yes, that's how you do X of L. How about X of C? 1 over 2 pi X, 2 pi F, C. That's where I messed up before. I was thinking increased capacitance, you increase the reactance too. You don't. You decrease the reactance, the capacitive reactance. Okay? Be careful of the units. Now they say use F, H, and omega. Okay? Farads represents capacitance. Henry's represents what?
Can you repeat that?
Okay? What does F stand for? Second? I can't hear. No, little f stands for frequency. That's a parameter. This is a unit. What unit does capital F stand for? capital L stand for? No? Done them on an earlier test.
Yeah, I thought it was.
What's that?
Fahrenheit.
That's if it has a degree in front of it.
Yeah, I know.
Okay, this doesn't have a degree. And we're not talking about temperatures.
I know.
What are we talking about? Yeah, I can't hear it. Okay. What's the title of this? That slide. What does the RLC stand for?
What is it? Reactive, resistant.
Resistors,
L is what?
inductors, and capacitors. Okay? That's three things. Here are three things. What you reckon those units stand for?
Resistance.
Which one?
I guess F is for resistance.
What's that again? I
Is
can't
F
hear.
for resistance?
What stands for resistance?
F.
F, really?
I don't know.
Yes, you do. We did it in Ohm's law. You did several tests with it. What do we measure resistance with?
Oh,
Ohms, of course. And which of those is an ohm?
the last one.
The last one. So resistance is measured in ohms.
Oh, well.
Say again?
And then which one was capacitance is measured in Henry, right?
No.
It was the inductor.
Inductors are measured in
Henry.
henries.
And so the capacitance is measured in F.
And what does that stand for? What scientist do we study early in this chapter? Faraday. Named after him, and that would be a second. What's the first five letters? Farad. That's why it's a capital F, because it's a farad named after Faraday. Henry is named after Henry, and ohms is named after ohms. But they couldn't use O because it would look like a zero. Okay? What would X of L be measured in?
X was what again?
Okay? Answer that. What does that stand for?
X stands for
The L stands for inductor.
okay, resistance. Not resistance, reactance.
Reactance.
X is for
So what is X of L measured in?
So we just said that.
Ohms. X of L is measured in ohms. What's X of C measured in? Second?
X of C was capacitance, and that was measured in farad.
C is measured in farads. Capacitance is measured in farads. What is X of C measured in? Second? No. Inductance is measured in henries. That's L. Ohms, it is. Your reactances and your resistances are measured in ohms. Okay? So, X of L is what?
X of L is the inductive reactance.
Right. X of C is?
Inductive capacitance. It's not in
What does X stand
Oh,
for?
reactance capacitance.
Other way. Capacitive reactance. Okay? Now, what were they measured in?
Oh.
Ohms. And R is measured in? Yes, of course. To find Z, what is Z called? Second, impedance. Okay, and what is it measured in? Ohms, of course, because you use the others to add them vectorially to be that. Okay, find the maximum current or the maximum voltage drop using Ohm's law. Okay, so you either know delta V max and you calculated Z so you can find I max, or you know I max, you calculated Z, you can find delta V max. Or you can use this same form but have RMS here and RMS there, or instantaneous here and instantaneous there. You can use any of them you want to in that form. Okay? Continuing, you then calculate the voltage drop across the individual elements using the appropriate form of Ohm's law and obtain the phase angle. What do we use to represent the phase angle? Second, what symbol do we use to represent the phase angle? So fun. I smell the blood of an Englishman. Go on to that. Phi. Phi, fo, fun. Yeah, that's old nursery rhyme. Okay, it's the phi. That's the little circle with the slash, vertical slash there. Okay? How do you obtain phi? Phase angle. See, phi's phase angle, they sound a lot alike. Start with the same sound. Picture it. What goes this way? In your phasor diagram, what is its horizontal?
The V of R?
Say again?
Are we talking about the V of R?
Not V of R.
R.
Okay. And then what else do you have in there?
The L is going up.
Okay, and?
The C is coming down.
Okay, it's not really L and C, it's X of L and X of C. It's the reactances, because they're all measured in ohms, right? Mm-hmm. And we write them, so if L is up, we write that first, X of L minus X of C. That would give you this part if X of L is larger, okay? And so you have your adjacent side and your opposite side. Here is the phi. So how is that phi related to those two?
I'm confused on the question.
You're confused by what?
The question?
Okay, it says obtain the phase angle. How? Don't you think you would use a phasor diagram? Okay, how does the phasor diagram go? What's the horizontal part of it? You answered it once before.
X of L.
No, it isn't. That's vertical. You answered that.
Oh, okay. The X of R then. That's
It's not X of R, it's just R.
Okay.
The only two with X's are capacitive and inductive. Those are reactances. R is just resistance. So the horizontal part is R. What's the vertical part? Okay, then how are they related?
How?
X of L and X of C. X of L pointing up, X of C pointing down, so how do you represent that?
It's a vertical line.
Yes, and how do you represent the length of it? The up part minus the down part. So down is negative, right? So that would be what? the up part? Okay, what's the down part? What's the difference in those? Difference means what operation? Subtract. What do you subtract from what? Say it. X of L minus X of C. That's your vertical part. Okay? Now, that forms an angle here. That's called phi, the phase angle. Now, how is that, the vertical part, the horizontal part, and the phase angle related to each other? Think trig functions. Say again? Tangent of what? That's it. Tangent of the phase angle, phi, is x of L minus x of C, the opposite side over the adjacent side, which is R. Okay? That's how you get your phase angle. Okay. Draw your diagram. Okay. Example 21.4, let's see what's next, is an RLC circuit, and you go through all those things we just said, and really a good thing to look at. Okay? 21.5, power in an AC circuit. Okay? No power losses are associated with pure capacitors and pure inductors in an AC circuit. Okay? Even though we say that they have X of L, which is a inductive reactance measured in ohms, still no power loss. And X of C, capacitive reactance, still no power loss. In a pure capacitor, during one half of the cycle, energy is stored in that capacitor, and the other half of the cycle is returned to the circuit. So it's just every half cycle, it stores, returns, stores, returns, stores, returns. So in a pure capacitor, there's no loss, no energy loss, no power loss. In a pure inductor, the source does work against the back EMF in the inductor, and energy is stored in the inductor, but when the current begins to decrease, the circuit, the energy is returned to the circuit. So, again, energy is stored, energy is returned, energy is stored, returned, just in an opposite order, kind of. Okay? So there's no losses, no power loss, no energy loss in pure capacitors or pure inductors. How about resistors? How about resistors? Okay, I'm saying, is there power loss in a resistor? Yes, that's exactly what a resistor does. It resists current, usually produces heat or something else like that, or does some sort of energy or something. So there is a power loss there. I prefer to say energy loss. I don't think they're being very precise when they say power loss. So, continue with this. The average power delivered by the generator is converted to internal energy in the resistor. The average power delivered by the generator is converted into internal energy in the resistor. Either it's producing heat, it's producing light, it's turning a circuit, it's doing your mowing your grass, whatever it's doing, producing heat in your iron, whatever. Okay? So this average power is your, what's the IRMS? What does that stand for? RMS. Root means square. And I stands for? for several chapters talking about I. What does it stand for? In Ohm's law, what does I stand for? Same I. What's that? I can't hear you. No. Instantaneous would be lowercase whatever. Instantaneous voltage would be lowercase v, delta V, and I can't say the other one. Okay. If you look at, this is just one place, equation 21.4a. You see that? Read it for me. Say again.
A series circuit consisting of a capacitor C connected.
Okay, right. Not figure. Equation 21.4a. In my book, it's on 690. I don't know if that'll be helpful or not. It's in section 21.1. About one page from the end of 21.1.
Oh, okay. The RMS voltage across the resistor is equal to the RMS current in the circuit times the resistance.
Okay. Say that again.
The RMS voltage across the resistor is equal to the RMS current.
And what does that stand? What does that RMS current? What's that?
You want me to review what RMS stands for?
Now, RMS, you already told me, root mean squared. What stands for current? I. That's what we're looking for, RMS current. So, P average, the average power, is the RMS current, root mean squared current. That's sort of your average current, you might say, times delta VR. That's the voltage drop across the resistor. Just the resistor, voltage drop across the resistor, which is also your RMS, which is root mean squared current, times the delta V, root mean squared voltage. Why? Because the voltage and the current are in sync here across the resistor, so that would just be your root mean squared voltage. Oh wait, I'm sorry, times the cosine of phi. What is phi? Okay, but what is it called? Phi is what follows a trig sum, a trig function. What do you operate on with a trig function? Okay, a tangent is a trig function. Cosine is a trig function. What do cosines and tangents operate on? Angles. And what angle? Okay. What angle are we talking about here? Well, it's the only angle we talked about in this chapter. It starts as phase angle. Phi stands for the phase angle. Now, we're not doing the tangent of the phase angle. We are doing the cosine of the phase angle. Okay? Now, get this. Look at it. I'll draw it here. I've got room to draw. Okay? Remember what goes on the horizontal part? R. What goes on the vertical part? XL. Minus X sub C. And this is what goes here. No. It has to have the same units of R's and X's. Say again? No, not delta X. Okay. That's
Oh, Z.
Z. What does Z stand for? Impedance. Okay. And what is this called? It's a phi. Phi, fi, fo, fum. Okay? Phi. Standing for? Phase angle, exactly. Phase, phi, they sound alike, right? Start with the same letters. Okay? Now, what we're doing here is P average is equal to root mean square current times the delta V across the resistor, which would be the root mean square current times the root mean square voltage difference and cosine phi. Well, cosine phi would be, look at this, cosine phi is what? Back from your trig class, cosine is? Cosine is? Caught another hen. Did you ever hear that? No, you didn't. Okay. That's the adjacent side over the hypotenuse. Remember that? And what is your adjacent side here? R over? Second? No, that's the opposite side. There's your right angle. What's your hypotenuse? Z. Okay, but that same phase angle, and I put a theta there, it should be a phi, is the one for and it's right there on page, I turn back, it's right here. That's also equal delta VR over delta VRMS. That's right there. It's not got an equation number, but on this section, 21.5, delta VRMS is equal to delta VRMS cosine phi. So instead of this, you put delta VRMS cosine phi. Okay? Just multiply this by both sides. And that's what delta VR is. So that's how you get that formula, average power. Where the quantity cosine phi is called the power factor. So depending on how big that phi is or how small, the smaller phi is, the larger the power factor. The larger phi is, the smaller the power factor. Because cosine starts at 1 and goes to 0. All right. So, okay. Wait, did I get it all? Phase shifts can be used to maximize power output. So what we try to do is adjust our X of L and X of C to maximize the power output. Okay? By getting that as close to 0 as we can. Because cosine of phi is 0, is 1 at 0, and phi is 0. So if we can make X of C and X of L equal to each other, you maximize the power. Okay. Now, moving on to example 21.5 is average power in RLC circuit, which is exactly what we were just describing. So it applies that we were just doing. So moving on to 21.6, resonance in a series RLC circuit. What do we mean by series? mean by series is you put one element after another element after another element. That's series. You put one element here and another element here, and there's energy, there's a path to each of them, that's parallel. When one path goes through them all, that's series. So this is resonance, and this just says an AC circuit. This is a series RLC circuit. So, resonance occurs at the frequency F0, I would call it F sub R, but they call it F sub 0, where the current has its maximum value. To achieve the maximum current, the impedance must have a minimum value. This occurs when X sub L equals X sub C, right? We've been saying that. If those two are equal, then the difference is 0. When the difference is 0, then you have everything is going through a resistor, okay? So that F sub 0 would be 1 over 2 pi times the square root of LC. Now, they don't tell you. They just pop that on you here. Let's see if the book does a little bit better job of that. Not really, okay? Not really. Oh, okay. Yeah, okay, they do a better job of it. Okay, if you remember, we're saying X sub L equal X sub C. What was, that's going to be true, when X sub L equals X sub C. Now, you told me just a few minutes ago, what is X sub L? It is the inductive reactance, okay? So, but what was the formula for it? Starts with F, L. Very good. And we're going to use that as F sub 0 now, okay? When that's equal to X sub C, and what is X sub C?
1 over 2 pi
Yeah, F sub 0 C, okay? Okay, my F is awfully ugly there. Let's see if I can clean that up just a little bit. Okay, cleaned up too much. Okay, now what we want to do is solve for F. So it looks like to me what we've got to do is multiply both sides of the equation by F sub 0. So that'll put an F sub 0 squared here and cancel out there. And we've got to divide by 2 pi. So that will make it, and divide by L. So that makes it F sub 0 squared is equal to 1 over 4 pi squared LC. Buy that? Okay, you divide both sides by 2 pi, and that makes 4 pi squared. Multiply by L, that puts the LC there. You multiply by F0 to get F0 squared here. Now you got F0 squared. What we're really interested in is F0, not F0 squared. So how do we get it? Take a square root. So we'll do that, and this becomes F sub 0 is equal to square root of 1 is 1, square root of 4 is 2, square root of pi squared is pi, and the square root of LC is the square root of LC. And that's exactly what they got there. So that's how we get it. Okay? Now, that's at your resonance frequency, and that's F sub 0, resonance frequency. All right. Now, the current reaches its maximum value at that resonance frequency, F 0. Okay? Now, and that maximum, this is IRMS is delta V RMS over Z. That's from our delta V RMS is equal to Z times IRMS. That's from there. Now, when you think about resonance in general. When you hear the term resonance, think about it, what does that imply to you? Do you think of anything with resonance? Okay? I don't know if y'all have ever done this. Have you ever tried to push off a car? Never. Okay. How about pushing a kid in a swing? Okay, how do you do that? To get maximum effect. When do you push? When they're coming up at you, you push?
When I'm coming back.
Okay, when they're coming back and reach right at the top, and just as they start to go down, then you give it a push. What you're doing, you're giving your push on the same frequency that the swing's doing. So you're resonating with the swing, and that gives you maximum effect. If you push any other time, it's not going to have as good of an effect, is it? You get maximum resonance when that happens. Okay. Now, why I asked the thing about car, literally, I can push off a car. I really convinced I am. And here's how you do it. And you could probably do it too. What you do is push as hard as you can and then relax. It's just like a swing. And when the car comes back at you, and just as it's starting to go again, you push again. And this time you add the natural move of the car forward to your push, and you get a little bit better, and then you swing back, and then you do it again. And every time, if you time it right, you soon get it going, and then all you have to do is keep pushing. Okay? You can push off a car that way. You can move lots of things that way. Okay? Is building up and adding to the resonance. Okay? That's kind of what we're talking about here. Where do you get the maximum? In other words, you get all the other things so it fits, so you maximize that current. That's what you're talking about. So theoretically, R is equal to 0. If R is equal to 0, the current would be infinite at resonance. Guess what? Real circuits always have some resistance. You can minimize it, but you can never eliminate it. Okay? Now, how do you tune a radio? You know? All you know is you turn a knob, don't you? And then you'll pick up whatever station you have to do. You hear some of them go by. Why are you being able to pick up stations by turning that thing? What are you doing there? What you're doing in that knob, remember we call them parallel plate capacitors, right? What you're doing, you're meshing two plates, but they're circular plates. Look at this. You're doing like this, and you're changing the capacitance of those plates by how you move and how much distance they have apart. That's called a varying capacitor. I've also heard it called a variable capacitor. A varying capacitor changes the resonant frequency of the tuning circuit of your radio to match the station to be received. Guess what? Right here in the air right now, there's probably tens, dozens, possibly even hundreds of radio signals right here in the room. Do you believe that? If you had a radio, you could just start turning the dial. You'd pick up one station after another station after another station. There's tons of those. All those signals are right here, right now. Okay? What you do to your radio, turning that knob, adjusts to the resonant frequency of each of those stations. And when you get it coming in good, you get the resonant frequency. So that's what you're doing when you're adjusting your radio. A metal detector does this. The portal is an inductor, and the frequency is set to a condition with no metal present. When metal is present, it changes the effective inductance, which changes the current, and that change in current is detected and an alarm sounds. That's how a metal detector works. Have you ever seen the people on the beach going along with those metal detectors, trying to find coins or other things that may have been dropped in the sand. That's exactly what's happening. I don't know if they give this example or not. No, they move on to transformers. Here's another example. I don't know if you've ever done it. I can't really illustrate it here, but I bet you where you live, I'm just making a guess, you have what they call, the brand name is sheetrock. It's called gypsum board on the walls. Do you know if you do? Okay. You don't have concrete block, do you? You have a sort of a smooth surface there, okay? And somewhere under that surface is probably a stud, a wooden stud. And that's what they nailed the sheetrock to, or the part of the gypsum board to, okay? Now, if you're trying to hang a picture that's sort of a heavy picture, you probably don't want to just go through sheetrock. You probably want to hit the stud. So they have these capacitors, and they're called stud finders. And what it's measuring is the resistance, or the impedance, or the capacitive reactance of that thing, and when you put it across, the light will come on or not come on. That lets you know where the stud is. And then you nail your nail there, or whatever. Same type thing as this. Those are, common name is stud finder. By the way, I forgot to mark the rest of the roll. Tia was here just briefly, wasn't she?
Yeah, she was here for Catholics.
That what?
She was here for Catholics.
Yeah, I know, but she was here this evening. Didn't she walk in right about the time the other class left? And then she turned around and walked right back out.
I didn't see that. I didn't see that.
Yeah, I think it was before you came in. It may have been before you came in, too. Okay. But I saw her. I don't think I'm imagining it. Okay. But the Applying Physics 21.1 was exactly this, metal detectors in the airports or other places like that. Courthouses have them, you walk through, and if you haven't taken out all the change or your keys or your watch or something like that, you set it off, and then they have to do the one thing. Okay, example 21.6, a circuit in resonance that's applying the very things we talked about. So, with that done, let's move on to transformers. What is a transformer? Now, there's several things that are called transformer. Some people call this box down here a transformer. In a sense, it sort of is. It transforms AC current to DC current. That's not what we're talking about here. What we're talking about here is an AC transformer. Strictly alternating current transformer. Not AC to DC transformer, but a strictly alternating current transformer. It consists of two coils of wire wound around a core of soft iron. Now, why do they say soft iron? Any idea? Does that mean you can push your finger into it? Does it poke that iron and scratch it or something like that? Carve your initials in it? No, iron is hard. What do they mean when they say soft iron? Think back to your electromagnetism chapter. You remember it? Electromagnetism chapter? You remember it? There were only 3 kinds of naturally occurring magnetic materials. What were they? Cobalt, nickel, iron. Okay, that's the most common one. Okay, cobalt and nickel are the 2 rare ones. Well, iron is easily magnetized, but also easy to lose the magnetism. That's called soft on magnetism. Okay. The nickel and cobalt and different alloys of them can be very hard to magnetize, but then they're hard to lose the magnetism. So they make great permanent magnets. So this is soft iron, meaning it makes a really good temporary magnet. as in electromagnet. Okay? Now, the side connected to the input AC voltage source is called the primary side, also called the primary coil, because it's two coils of wire. I often call it the primary coil, and it has N1 turns. That's just the number of turns there. So here would be the one connected to the, and what kind of voltage? What kind of voltage? AC. It's got to be AC. Okay? And here's why. So here we have this coil around the soft iron core, right? Now, what happens when you do alternating current? Tell me what alternating voltage. Alternating voltage does. It goes up and down and up and down and up and down. So you have constantly changing voltage. Here you have a coil. What that does, a changing current, changing charge, moving charge, induces what? A moving charge induces, especially a changing charge induces a, we did this in lab with that circuit board, that trainer that we had from Toyota. Moving charge or a changing electric field induces a magnetic field. Remember? Changing electric. And this is always changing, going plus, minus, plus, minus, plus, plus, plus. So therefore, you're inducing a changing magnetic field here. And the more coils you have there, the stronger the magnetic field, right? Okay. So here on this side, this is called the secondary or the output coil. Okay? And over here, you have a different number of coils. This one actually shows N2 being greater than N1. What is that going to do for you? Whatever your voltage was here, this steps up the voltage because you have more coils here. Okay? So your delta V here is greater than delta V1 there because you had more coils. Coils in N2 was greater than N1. Okay? So the AC voltage delta V1 is applied to the primary coil. The output voltage delta V2 is observed across the load resistor, whatever you have out there, and that's the secondary coil, secondary circuit, the output circuit, output coil, whatever you want to call that, and the voltages differ by the ratio of the number of turns or coils. Okay? So let's get to the next slide. Oh! Let's see if we can finish this slide. Okay? The other side, called the secondary coil or secondary circuit, is connected to a resistor. It has N2 turns. The core is used to increase the magnetic flux and to provide the medium for the flux to pass from one coil to the other. The rate of change of the flux is the same in both coils because they have the same core. Okay? Now, here's how the voltages are related. Okay? You can do this several ways. This is one way. I like this a little better this other way. Let me show you how I like to do it. Okay? And it doesn't matter how you do it, but delta V2 over delta V1 is equal to N2 over N1. Set up a proportion like that. You see? The same order. The voltage 2 to voltage 1 is the ratio of the number of turns in 2 and the number of turns in 1. You see how to do that? And then if you're solving for delta V2, which usually you are, you just multiply both sides by delta V1. And that's how they got this equation here. But I like to see where they got it. Okay? Now, when the N2, the number of coils on the secondary side, is greater than the number of coils in the primary side, this is called a step-up transformer, because you're increasing the voltage on the output side, right? If the number on the secondary side is less than the number of the primary side, the transformer is referred to as a step-down transformer. Now here's why. Guess what? The power is the same. You can't create or destroy energy. Okay? Now, do you remember the equation or the formula for power? This is way back in an earlier chapter. What is power? Of energy. Okay? And we could from that do, but we don't have much time. Let me just give it to you. It's current times voltage. Power is IV. P is equal to IV. Current times voltage. Right? Now, the power is the same. P1 is equal to P2. You can't change the power. But if you change the voltage, increase the voltage by stepping up the voltage, guess what you do? You have to drop the current because the product is the same. You got it? So if you step down the voltage, that steps up the current. Now, at the generating plants, out there at the power station, or the hydroelectric plant, wherever it is, you're producing power, right? Energy per unit time, right? Now, you want to send that energy all the way into Birmingham or Bessemer or wherever, right? Right? Now, if you're sending that long distance, then you have a great deal of line loss. Now, what contributes to the line loss? Voltage or current? What contributes to the line loss? Voltage or current? What contributes to the line loss? Voltage or current? No, the current. The current is what produces heat. That's your loss of energy. Okay? So if you can cut down the current, you reduce the amount of energy you've lost in transmission. So what you want to do at that power plant, you want to step up the voltage as high as you can get away with and step down the current. Okay? Because those go together. However, when you get into town, and you've probably seen these big blocks where they put the wire fence around and everything and keep people out of there, they have these great big old transformers there that step down the incoming voltage to something lower. And then before it gets to your house or your apartment, go out and look at where the power lines come in. And I bet you'll see, hanging on a power pole, the one closest to your house or apartment, you'll see a big cylindrical box there. Take a look and see. That is the last step down transformer. You're stepping down the voltage that got it to your house to the voltage you'll use in your house, stepping up the current so you can run all your devices. You don't want a high voltage in your house. You want low voltage and reasonable current. So that's what you're doing with that. You're stepping up voltage at the power plant, stepping down voltage before you use it. Okay? And sometimes even before it comes into town. Okay? The power input into the primary equals the power input output at the secondary, and again, power is I delta V. Yes. I'm sorry?
I think we're out of time.
I know, but I'm going to finish the slide, okay? I1 delta V1 is equal to I2 delta V2. Power in equal power out, right? You can't gain or you can't create or destroy energy. And this is energy per unit time. If the secondary voltage, this voltage is higher, that means the secondary current must be lower. You don't get something for nothing. This assumes an ideal transformer. In real transformers, the power efficiencies typically range from 90 to 99%. So they're usually pretty effective. Okay. That is where we'll stop and pick up. Whoa. I don't see transmission. So this must be, all right. We'll go over this. I guess that's just not a slide. And this is a long chapter, isn't it? Goodness gracious. Okay. So we'll pick up there next time. I don't even know where to mark it in my book. There it is, power line transmission. Okay. I'm going to turn this off